This tool shows the methodology and database for Mercury-Injected Capillary Pressure data, or MICP for short. The database shows globally derived data which cover most geological time periods, different depositional settings, different diagnetic alterations, different geographic areas and different burial depths. MICP data are important for predicting water saturation in a reservoir. The data has to be converted from a mercury air to an oil-water system, and this conversion is dependent on contact angle and surface tension. Different methodologies for averaging MICP curves are applied in the oil and gas industry, of which the levered J-function and Thomire methods are the most common. A new averaging method, denoted as the Lonoy method, is applied in CARP. The Lonoy method is based on a large global MICP database, currently consisting of approximately 700 measured MICP curves, which shows the empirical relation between pore types, porosity, capillary pressure and mercury saturation. The database covers 19 of the pore types published by Lonoy 2006. Samples in the database are grouped according to pore type and mercury porosity interval. Porosity intervals are from 0 to 5%, 5 to 10% and usually up to 25 to 30% or 30 to 35%. For chalk, the porosity interval extends up to 45 to 50%. The number of samples within each group may vary considerably, from no samples to tens of samples. The MICP curves within each group are averaged, and a power trendline and associated trendline equation for each group is defined. Here we see an examples for porosity interval 15 to 20% of pore type 4.12. The trendline is defined for capillary pressures up to 2000 psi, which is the blue part of the curve. Higher pressures equivalent to oil capillary pressures exceeding 145 psi are believed to represent irreducible water saturation, and have therefore been excluded from the averaging process. For this group, 50 to 20% porosity for pore type 4.12, the 10 samples in the database have an average porosity of 17%. For each pore type, a trendline for every 5% porosity interval is defined. In order to reduce the number of equations and to apply porosity as a continuous variable parameter, an optimal composite equation was calculated for each pore type. This means that we are merging all trendlines for a pore type into one equation. Pore type is one of the most important parameters controlling reservoir quality. Pore types are controlled by sedimentologic and diagnetic processes, and pore type distribution can thus be inferred regionally from phases maps. This means that MICP curves can be applied at cell grid resolution in reservoir models, based on phases or pore type distribution maps and porosity distribution. The tool consists of two parts, MICP curves and mercury capillary entry pressures, which we find on the menu. We will start with the MICP curves. Input areas are marked by yellow background color. Pore types can be selected from the radio buttons to the left, and porosity intervals can be selected from the radio buttons to the right. The average measured MICP curve for each porosity interval and pore type is given as the green curve. Predicted MICP curves based on the levered, Thomire and Lonoy methods are plotted as blue, black and red curves respectively. The Leverett and Tomir methods require permeability as input, and Tomir additionally requires capillary entry pressure. These input parameters have been predicted from other prediction tools in CARP. The Lonoi method, which is a new methodology developed by Lonoi Geoconsulting, does not require permeability or capillary entry pressure, but is based solely on pore type and porosity. Additional information given on the plots are the number of samples n for each pore type and porosity interval, the average porosity of the global data set within each porosity interval, irreducible water saturation sphere in an oil-water system. This has been arbitrarily defined at mercury capillary pressures exceeding 2000 psi. This is equivalent to oil capillary pressure of approximately exceeding 145 psi. The average deviation of predicted MICP curves using Leverett, Tomir and Lonoi methods as compared to average measured MICP curves are also given. The deviation is given for each pore type and porosity interval and is given as the absolute logarithmic value of mercury capillary pressure for each 5% mercury saturation. Two cutoffs are applied. To the left here we have applied sphere as a cutoff, and to the right we have applied a combination of sphere and a mercury saturation of 75%. Deviations are given for both porosity interval and pore type. Let us proceed to mercury capillary entry pressures. This part displays the CARP database on mercury capillary entry pressures as derived from the MICP curves. The entry pressures are presented as average values for each pore type and pore type group and for each 5% porosity interval. Input areas are marked by yellow background color, and pore types and pore type groups can be selected from the radio buttons. For each pore type, the average porosity is given on the x-axis, and the number of samples are given as orange bars. The average mercury capillary entry pressures for each 5% porosity interval are plotted along with trend lines and associated coefficient of determination R² for each pore type and pore type group. The total number of samples within each pore type or pore type group are given in the green text box.